Now in the last lecture we had discussed regarding the kinematics of rigid bodies with respect to the relative analysis for the second case where omega is not equal to omega bar. Okay, there is a relative motion involved. Okay, and we had seen the equations for velocity and acceleration for this particular case. The velocity v capital xyz is given as v small xyz plus r dot vector plus omega vector cross rho vector. This was the equation for velocity, and the equation of acceleration was a capital xyz vector equal to a small xyz vector plus r double dot plus 2 omega vector cross v small xyz plus omega dot cross rho vector plus omega vector cross omega vector cross rho vector. So this was the equation for velocity and acceleration as we had derived in the earlier lectures. Now today we will do some of the problems in a case of relative motion. Now here is a question. Okay, this question is from Hibbler. Rod AB rotates clockwise such that it has an angular velocity omega AB equals 3 radians per second and angular acceleration alpha AB equals 4 radians per second square when theta equals 45 degree. Determine the angular motion of rod DE at this instant. The collar at C is pin connected to AB and slides over rod DE. Now in this question you can see two corresponding rods here, AB as well as DC, which are undergoing and angular velocity and acceleration. Okay, the corresponding angular velocity and acceleration of the rod AB is given to you. Omega AB is equal to 3 radians per second and alpha AB is equal to 4 radians per second square. Now this collar is able to slide along the rod DE, but it is pinned with respect to rod AB. Okay, that you have to remember in mind. Okay, this collar, it can slide over the rod DE, but it is pinned with respect to rod AB. Or in other words, this collar will undergo pure rotation with respect to the point A. This is one important point you have to remember. Okay, now the question is, at a particular instant of theta is equal to 45 degree, okay, what is the corresponding value of omega DE and alpha DE? Okay, that is what we have to find out. So whenever a question is given to you of a relative analysis in kinematics of rigid bodies, or the first step is to fix the reference frames. We have the capital XYZ reference frame and the rotating reference frame small xyz. So first you will have to fix both of these. So since this is a question of planar motion, I'll take only xy axis. So I will fix my xy axis somewhere to the ground. Let me say it is xy here, somewhere here. Okay, and I will fix my secondary reference frame small xy, say somewhere here like this. Now this xy as such is embedded within DE and it will undergo an angular velocity omega DE and an angular acceleration alpha DE. Okay, so the question is to find omega DE and alpha DE. Okay, so in the equations, I hope you remember the equations. V capital XYZ is equal to V small xyz plus r dot plus omega cross rho vector. Okay, so as such the velocity vxyz is the velocity with respect to the primary frame xy is equal to velocity small xyz, that is velocity with reference to the secondary frame xy, and r dot vector plus omega. Here omega is omega de. Okay, here omega means this secondary reference xy is rotating with respect to capital xy, okay, with an angular velocity omega. So here omega is equal to omega de. Okay, and similarly the acceleration vector a capital xyz is equal to a small xyz plus r double dot plus 2 omega vector cross v small xyz plus omega dot, or I can write it as alpha vector cross rho vector plus omega vector cross rho vector. Okay, so here alpha vector as such, alpha vector, it is alpha de vector. Okay, so this you have to remember in mind. Okay, the first step in any questions related to kinematics of rigid bodies is to fix the reference frames capital xyz and small xyz properly. Now first we will express omega de and alpha de in vector format. Now you can see that this AB as such is undergoing a clockwise rotation as such. So this rod DE will also be undergoing a clockwise rotation. So based on that we can write the vector omega DE and alpha DE in terms of their magnitudes. So I will first write that omega DE vector is equal to the magnitude omega DE into, now since it is clockwise rotation, okay, the corresponding direction of the angular velocity will be in the negative z direction, that means into the paper. So I can write this minus omega de into k cap radians per second. Similarly alpha de vector is equal to minus alpha de into k cap radians per second square. Now the values which are already given to you are omega AB, it is given as 3 radians per second, that is also clockwise, so as such it will be minus 3k radians per second, and alpha AB is also given to you, it is also clockwise as such, so it will be minus 4k radians per second square. So this is how you express the corresponding vectors in terms of their magnitudes. Now the first step here is understanding the motion of the collar relative to capital XYZ. Now in this figure you can see that this corresponding collar will be undergoing a pure rotation with respect to the point A. Okay, it will be undergoing pure rotation with respect to point A. It will be sliding over rod DE, but it will undergo pure rotation with respect to the rod A, with respect to point A here. So I can get velocity and acceleration of this collar with respect to the primary frame or the fixed frame XY. Remember this statement very carefully. Okay, this corresponding collar, okay, this collar here is undergoing pure rotation with respect to point A. Since point A is fixed, it is like saying that we can get the velocity and acceleration of the collar C with respect to capital XYZ. Okay, so here velocity with respect to capital XYZ is equal to Now if this corresponding collar C is undergoing pure rotation with respect to the point A, I can write the equation of velocity as omega AB vector cross R AC vector. Okay, see the figure here, omega AB cross RAC. This will be equal to minus 3 k cap cross now RAC vector. Okay, if you see the figure here, okay, with respect to point A, the collar C at that instant of time will have an ordinates along x-axis as 0.4 and along y-axis as 0.4. So as such, RAC is equal to 0.4 I cap plus 0.4 J cap. Now if I solve this, I would get 1.2 I cap minus 1.2 J cap. Now I can obtain the acceleration with respect to the fixed frame AXYZ. Okay, as you already know, since it is a case of pure rotation, you can write the acceleration vector as alpha AB cross RAC plus omega AB cross RAC vector. This equation we had already studied in the case of pure rotation in lecture 19. Okay, so as such, if I substitute the values, I would get minus 4k cross 0.4 I plus 0.4 J. Now since it is a case of planar motion, omega AB cross RAC can be written as minus omega AB magnitude square multiplied by RAC vector. Okay, so as such, this will be equal to, if I multiply this, I would get minus 4k cap cross 0.4 I cap plus 0.4 J cap minus omega AB is having a magnitude 3, so 3 square into 0.4 I cap plus 0.4 J cap. So if you solve this equation, you would get minus 2 I cap minus 5.2 J cap meter per second square. This is meter per second. So as such, we had obtained the absolute value, absolute velocity and acceleration of the collar with respect to the primary reference frame or the fixed reference frame capital XYZ. Okay, now we will look into the motion of the small xyz relative to capital XYZ. Here is where we apply the equations which we had studied earlier. So V capital XYZ is equal to V small xyz plus R dot plus omega vector cross rho vector. In this, V capital XYZ we had already obtained from the previous relation. Now V small xyz is equal to, now you see in the figure here, the collar C here with respect to the secondary reference frame small xy or with respect to point D. Okay, suppose that magnitude is V small xyz. Okay, so as such, with respect to small xyz, my velocity vector will be equal to v small xyz magnitude multiplied by I dash. Okay, where the corresponding I dash vector is with respect to small xyz. But at this instant of time here, DE is horizontal. That means the small xyz and the capital XYZ are oriented in the same direction. Okay, so as such, I can write this as Vxyz into I cap. Okay, at that particular instant. That is what we are always finding, everything with respect to an instant of time here. Okay, so V small xyz is equal to the magnitude Vxyz into I dash. Okay, that is with respect to small xyz. So I can change it with respect to capital XYZ, since at that instant I dash and I are in the same direction. Okay, now r dot vector. R dot vector is the velocity of the secondary reference frame small xyz with respect to capital XYZ. Let me tell you again, if you remember it early, r vector is this vector. R vector is this vector. Okay, so r dot is the velocity of small xyz with reference to capital XYZ. But you see, this small xyz does not translate. Okay, it simply rotates with respect to the point D. Okay, as the rod DE rotates, okay, this small xyz will rotate along with it since it is embedded. So as such, r is fixed. Okay, so r dot will be equal to 0. So in this equation, r dot is equal to 0. Next, so we had looked into the terms v capital XYZ, v small xyz, r dot, and omega vector as such is omega DE vector, which we had already obtained it as minus omega DE into k cap. And rho vector as such is the position vector of the collar C with respect to the secondary reference frame small xy. Okay, so this is at a distance of 0.4, so I can write this as 0.4 into I dash. Okay, 0.4 into I dash. But since at that instant of time both small x coordinate and capital X coordinate are aligned along the same direction, this will be equal to 0.4 into I cap. Okay, now simply substitute all these in the corresponding equation. Now v capital XYZ we are already obtained from here. So as such, I'll substitute it here. 1.2 into I cap minus 1.2 into j cap is equal to, just let me draw a line here so that you don't get confused. V vector, v small xyz vector is equal to, from here you can set that magnitude Vxyz into I cap plus r dot vector is 0 plus omega vector is omega DE, that is equal to minus omega DE into k cap cross rho vector, that is equal to 0.4 into I cap. So this will be equal to V xyz into I cap. Now if you take the cross product of these two, you will get minus 0.4 omega DE into j cap. Okay, now equating the left hand side, and the right hand side, you will get, we'll equate the magnitudes of I and j cap respectively. So you will get v small xyz is equal to 1.2 meter per second and 0.4 omega dE is equal to 1.2, or omega dE is equal to 1.2 divided by 0.4, that is equal to 3 radians per second. Both of these are magnitude, okay? Both of these are magnitude and not vectors. So I'll write it here, the vector notation. V small xyz vector is equal to 1.2 into I cap, and omega dE vector is equal to minus 3 into k cap. So as such, we had obtained the velocity with respect to small xyz and the omega dE vector. Omega dE vector. Similarly, you can find the acceleration also. The equation of acceleration, a capital xyz is equal to a small xyz plus r double dot plus 2 into omega cross v small xyz plus alpha cross rho vector plus omega cross rho vector. So as such, we look into each of these terms. The absolute velocity a capital xyz, we had already obtained it earlier, okay? We had got it is equal to minus 2 I cap minus 5.2 j cap. Okay, I'll write it here on this side. A capital xyz is equal to minus 2 I cap minus 5.2 j cap. Okay, a small xyz. Now as such, I told you I can write this as a xyz into I dash vector. Since since at this particular instant of time, both the small x and capital X are oriented in the same direction, I can write this a xyz into I cap. Okay, this is I dash cap and this is I cap. Now next, r double dot. I told you the small xyz reference frame is not translating with respect to the capital xyz. So as such, this is equal to 0. And omega as such is equal to omega dE vector. Okay, that is equal to minus omega dE into k cap. Okay, now v xyz we have just obtained before, the value, it is 1.2 into I cap. So this is 1.2 into I cap. Next, alpha vector, that is equal to is alpha dE vector. We can represent it as minus alpha dE into k cap. Okay, and finally the rho vector, which is equal to 0.4 into I dash cap is equal to 0.4 into I cap. Okay, so substituting all of these here, you will get minus 2 I cap minus 5.2 j cap is equal to a xyz into I cap plus 0 plus 2 into minus omega d. Now omega dE we have already obtained it. Okay, so I can write this as minus 3. Okay, so minus 3 k cap cross 1.2 I cap plus alpha. I'll write it as minus alpha dE into k cap cross rho vector, it is 0.4 into I cap. Now since this is a planar motion, okay, omega cross rho, I can write it as minus 3 square into rho, that is 0.4 into I cap. Okay, now if you take the cross product and solve this out, you would get a xyz into I cap minus 0.4 into alpha dE into j cap minus 3.6 into I cap minus 7.2 into j cap. Now this will be equal to, I'll equate the common terms, a xyz minus 3.6 into I cap plus minus 0.4 alpha dE minus 7.2 into j cap. Now equating both sides, we get a xyz minus 3.6 is equal to minus 2, or I can say a xyz. Now a xyz is only the magnitude, that is equal to 1.6 meter per second square. Now minus 0.4 alpha dE minus 7.2 is equal to minus 5.2. From this I'll get alpha dE is equal to 5 radians per second. See the question once again. Okay, you have to find the angular motion of rod dE. So as such, express omega and alpha in terms of the vector format. Okay, so as such, I'll write this once again. Omega dE vector is equal to minus 3 into k cap and alpha dE vector is equal to minus 5 into k cap. Radians per second square. This is radians per second. I think in the previous one I missed second square. Okay, this is radians per second square. So I hope you understand. There is nothing complicated here. Okay, the thing is that we will have to fix the primary reference frame and secondary reference frame appropriately. Understanding that concept will require some time. Once you do 2-3 problems, you will get to know that. Now moving on to the next question. The disk rotates with an angular motion shown. Determine the angular velocity and angular acceleration of the slotted link AC at this instant. The peg at B is fixed to the disk. Now see in this figure here, you have a corresponding disk here and you have a peg that is attached to the disk. And this disk is undergoing an angular velocity omega equals 6 radians per second in the anti-clockwise direction and an alpha equals 10 radians per second in the anti-clockwise direction. Okay, so I can say that this peg here, since it is fixed to the disk here, this peg is undergoing pure rotation with respect to this point here. Okay, let me say this point is O for the time being. Okay, so it is undergoing pure rotation with respect to the point O. Now since this corresponding peg is within the slotted link here, as this disk moves, the link AC will also rotate. Okay, link AC will also rotate. So our aim is to find the corresponding angular velocity and acceleration. Okay, angular velocity and acceleration of this link AC. So we have to find omega AC and alpha AC. This is the term we'll have to find it out. Now as I told you, first you have to fix the primary and the secondary reference frames. Okay, since this is also a case of planar motion, okay, so I will fix my primary or fixed reference somewhere here, and I will fix my secondary reference frame xy like this, okay, such that it is embedded within the body AC, within the link AC, and it rotates with respect to the primary frame capital XY. Okay, now in the question, the angular velocity and acceleration of this disk is given. So as such, I can obtain the velocity and acceleration of this peg B with respect to point O. Or in other words, since point O is fixed, I can say that it is with respect to the fixed reference frame capital XY. I can write angular velocity and acceleration of OB. Okay, so I'll write it as here. Omega OB vector will be equal to, you see, this is undergoing an anti-clockwise direction. So as such, the direction of the angular velocity will be outwards from the plane of paper along the z direction. So this will be equal to 6 into k cap radians per second. Similarly, alpha OB vector will be equal to 10 k radians per second square. Now we have to find the velocity and acceleration of the peg B with respect to point O. But since point O is fixed, it is like saying that we are finding the velocity and acceleration with respect to the fixed reference frame capital XY. Okay, so I'll write it here. Motion of peg relative to capital XYZ. So V capital XYZ vector is equal to, okay, you know the equation in case of pure rotation, omega OB vector cross ROB, which is equal to, now omega OB vector we have already obtained it, it is 6k vector cross ROB vector. See this figure here, ROB vector, you see OB is inclined at an angle of 30 degree with respect to the horizontal, okay, and the length of OB is equal to 0.3 meters. So I can write ROB vector as 0.3 into cos 30 into I cap plus sine 30 into j cap. Now this, if you multiply, you will get 0.26 I cap plus 0.15 j cap. Substituting in this equation, 0.26 I cap plus 0.15 into j cap, we'll obtain it as 1.56 j cap minus 0.9 I cap, or I can write this as minus 0.9 I cap plus 1.56 into j cap. Similarly, you can obtain the acceleration with respect to the capital XYZ frame, because the peg B is purely rotating with respect to point O. So this will be equal to alpha OB vector cross ROB vector plus omega OB vector cross omega OB vector cross R OB vector. Now alpha OB vector we are obtained as 10k cross R OB vector 0.26 I cap plus 0.15 j cap plus omega OB vector cross omega OB vector cross R OB. I can write it as minus omega OB square into R OB vector. So this multiplied, you will get k cross I, you will get j. So 2.6 into j cap, k cross j minus I, so minus 1.5 into I cap minus omega OB magnitude, it is 6 square into 0.26 I cap plus 0.15 j cap. So if you solve this, you would get minus 10.86 I cap minus 2.8 j cap. So here I had obtained the corresponding motion of the peg relative to the primary reference frame capital XYZ, because as such the peg is rotating with respect to a fixed point O. Next, our step is to find the corresponding motion of small xy relative to capital XY. Okay, the secondary reference frame relative to the fixed reference frame capital XY. So let me write that. Motion of XYZ relative to capital XYZ. Okay, so you know the equation, we have studied it earlier. V capital XYZ vector is equal to V small xyz plus R dot plus omega cross rho vector. Now here again we look into each of these terms. Okay, V capital XYZ we have already obtained it earlier, that is equal to minus 0.9 I cap plus 1.56 into j cap. Now V with respect to small xyz is equal to, you see here, now the small xy frame here is embedded within the link AC here. Okay, so as such, with respect to the small xyz, this peg is having a velocity along the link here. Okay, either it may be towards the right or it may be towards the left. Now at this instant of time, when the angle is at 30 degree and the disc is rotating at an anti-clockwise direction, this peg B with respect to the link AC will be moving towards A. At this particular instant, this corresponding peg will be moving towards the point A. Okay, so as such I can write this Vxyz as minus magnitude of Vxyz into I dash cap, where I dash is the corresponding unit vector along the secondary x-axis. Okay, remember one thing, this secondary xy frame is embedded within the link AC. Okay, now let us try to express this I dash in terms of I and j, in terms of the unit vectors along the primary axis. Now if you see this figure, I and j are fixed. Okay, and I dash and j dash will keep on rotating with the rotation of the link here. So at this instant, when this angle is 30 degree, if I express it, I would get I in this direction, j in this direction, and I dash is in this direction at this particular instant, and this is j dash. The inclination with respect to the vertical here, it is 30 degree. Okay, so here I can express I dash in terms of I and j here. Now this will be equal to minus v xyz into sine 30 into I cap minus cos 30 into j cap. Sine 30 into I cap minus cos 30 into j cap. So this, if I solve it, I will get minus vxyz 0.5 I cap minus 0.867 j cap. Now the next term here is r dot vector. As I told you, r dot vector as such will be 0, since the corresponding origin of the secondary frame A is fixed with respect to the fixed frame capital XY. Now the next term is omega. Omega, as you know, is omega AC, which I can write in terms of magnitude as the rotation here, it is in clockwise direction at this particular instant. If you see this figure, at this particular instant, the corresponding rotation of this link AC will be in anti-clockwise direction. So as such, this will become omega AC into k cap. Okay, and then the row vector. The row vector here, if you see this figure here, at this particular instant, this point or this peg B is a distance of 0.75 from the origin of the secondary reference frame small x small y. So as such, I can write row vector as 0.75 into I dash cap, which if I express in terms of the unit vectors along the fixed frame, I would get 0.75 into 0.5 I cap minus 0.867 j cap. Now if I substitute all of these values in the equation here, I would get minus 0.9 I cap plus 1.56 j cap is equal to minus vxyz into 0.5 I cap minus 0.867 j cap plus 0 plus omega AC into k cap cross 0.75 into 0.5 I cap minus 0.867 j cap, which will give me minus 0.5 vxyz into I cap plus 0.866 vxyz into j cap plus 0.375 omega AC into j cap plus 0.65 omega AC into I cap, which will be equal to minus 0.5 vxyz plus 0.65 omega AC into I cap plus 0.866 vxyz plus 0.375 omega AC into j cap. Now equating the terms, minus 0.5 Vxyz plus 0.65 omega AC is equal to minus 0.9 and 0.866 Vxyz plus 0.375 omega AC is equal to 1.56. So if you solve this both, you would get omega AC is equal to 0 and Vxyz is equal to 1.8 meter per second. That means Vxyz vector is equal to minus 1.8 into 0.5 into I cap minus 0.866 into J cap. The next step is to find the acceleration. So we have the equation A capital XYZ is equal to A small xyz plus R double dot vector plus 2 omega cross V xyz plus omega dot cross rho vector plus omega cross rho vector. Okay, so this is the equation. Now the terms, if I come to the terms, omega vector is actually omega AC vector, which we had obtained as 0. Okay, then R double dot will also be equal to 0. Then AXYZ vector as such, similar like the earlier term of Vxyz, here AXYZ will be equal to minus the magnitude of AXYZ. Now if you express in terms of I and j, it will become 0.5 I cap minus 0.866 j cap. Okay, and then omega dot vector as such, we don't know the value. It is, so omega AC vector I'll write in terms of alpha. Okay, so now alpha AC also I'll assume it to be in the anti-clockwise direction, so I can represent it as alpha AC into k cap. Next, the rho vector. Okay, the rho vector is 0.75 into 0.5 I cap minus 0.866 j cap. And finally, you have the corresponding A capital XYZ, which we had obtained it earlier, that is equal to minus 10.86 I cap minus 2.8 into j cap. So substituting all of these here, you would get minus 10.86 into I cap minus 2.8 into j cap is equal to A small xyz, that I can write as minus A small xyz into 0.5 I cap minus 0.866 j cap plus R double dot, that is equal to 0, plus 2 omega cross Vxyz, or if omega is omega AC, so that is also equal to 0. Then you have omega dot cross rho vector, so that will be equal to alpha AC into k cap cross 0.75 into 0.5 I cap minus 0.866 j cap. Then the last plus omega cross rho, since omega is equal to 0, so that will also be 0. So as such, if you try to equate, if you solve this equation and try to equate the terms, you would get minus 0.5 AXYZ plus 0.65 alpha AC is equal to minus 10.86. 0.866 AXYZ plus 0.375 alpha AC is equal to minus 2.8. So solving, you will get AXYZ is equal to 3 meter per second square and alpha AC is equal to minus 14.4 radians per second square. So as such, alpha AC will be equal to, alpha AC vector will be equal to minus 14.4 k cap. That since it is minus 14.4, it indicates that the corresponding angular acceleration will be clockwise, even though we had assumed it to be anti-clockwise. Okay. This is how you solve this problem. Moving on to the next question. A truck is moving at a constant speed v equals 1.7 meter per second at time t. The truck loading compartment has at this instant a constant angular speed theta dot of 0.1 radians per second at an angle theta equals 45 degrees. A cylinder of radius of 300 mm rolls relative to the compartment at a speed omega of 1 radians per second, accelerating at the rate omega dot of 0.5 radians per second square at time t. What are the velocity and acceleration of the center of the cylinder relative to the ground at time t? The distance d at time t is 5 meter. This question is from James. This question is one step ahead, where the number of calculations involved are much more compared to the other two questions. So first let us see what corresponding values have already been given to you. Now here in this figure you can see the loading compartment here, that is rotating at an angular velocity theta dot, that is given to you 0.1 radians per second. Now the cylinder here rolls down with an angular velocity omega 1, that is given as omega 1 equals 1 radians per second, and then it has got an acceleration omega 1 dot, that is equal to 0.5 radians per second square. Now the first step as such, once we write the given data, is to fix the primary and the secondary coordinate systems, primary and secondary reference systems. So as such, I will fix my primary reference system onto the ground, represented by capital X and Y. And since I am concerned with the motion of this cylinder here, I will fix the secondary reference frame to the floor of this loading compartment. So this is the y-axis and this is the x-axis. Okay. Now once I fix the reference frames, I will express all of these in terms of vectors. So theta dot as such I can represent in terms of vector here. You see this corresponding loading compartment is undergoing clockwise rotation. So as such, in vector format this will be equal to minus 0.1 into k cap. Okay, and then omega 1 vector here, you see in this figure here, omega 1 also undergoes angular rotation in the clockwise direction. So as such, I can also write this as minus 1 into k cap, and omega 1 dot vector will also be in the clockwise direction. So minus 0.5 into k cap. So these are the corresponding vector formats of the data that is given to you in the question. Now remember one thing here, the fixed frame xy and the secondary reference frame small xyz have both their z axis that is perpendicular to the plane of this computer, of the screen. So as such, k will be equal to k dash. Now the question here is to find the velocity and acceleration of the center of the cylinder relative to the ground at time t, and during that time t the corresponding distance traveled d is 5 meters. So what is the velocity and acceleration at an instant of time when d equals 5 meters, or d when this corresponding cylinder reaches almost the end of the loading compartment? That is what the question is. First, we shall be concerned with the motion of the center of the cylinder. The question is to find the motion of the center of the cylinder. So motion of the center of cylinder. Now let rho represents the position vector of the center relative to the small xy. So position vector of center relative to small xy reference. So that corresponding rho vector, you see, as such it will be directed along the secondary y-axis here. So I can write rho as 0.3 into j dash cap, okay, which in terms of meter. Now I can represent j dash in terms of the unit vectors of the fixed reference capital X capital Y. So let me draw it here. You have xy fixed coordinate xy here. Now at a particular instant of time when the corresponding angle is theta, when the corresponding theta equals 45 degree, the orientation of the secondary coordinate will be like this. So this angle here will be equal to 45 degree. So I can represent j dash is equal to cos 45 into I cap plus sin 45 into j cap. That is equal to 0.707 I cap plus 0.707 j cap. So I'll convert it right here itself so that it becomes easier for me. So 0.3 into 0.707 I cap plus 0.707 j cap, which will be equal to 0.2121 I cap plus 0.21 j cap. Next, we will find the velocity of the cylinder with respect to the secondary reference frame xyz. So here I can write motion of the center of cylinder relative to small xy. Okay, so that you can understand this one. It is relative to small xy here. So the velocity vector, this is also a vector here. The velocity vector relative to the secondary reference here will be equal to. Now you see this figure here. Secondary reference frame here is attached to a point when the value of d is 5 meters. Okay, so as such that position will be slightly downward when d equals 5 meters. In that case, the center of the cylinder will have only rotation. So as such, I can express the velocity with respect to the secondary reference frame small x small y as omega 1 vector cross rho vector, which will be equal to minus 1 k cap cross 0.21 I cap plus 0.21 j cap. So if you solve this, you will get 0.21 I cap minus 0.21 j cap. Now the acceleration of the center of the cylinder relative to the secondary reference frame small xy can be expressed as alpha cross rho vector, or I can write this as omega 1 dot vector cross rho vector. Okay. Now usually people have a confusion here. You must have studied that for a body that is undergoing rotation, the acceleration vector axyz is equal to alpha cross r plus omega cross r. But here there is a difference. Here we are finding the corresponding acceleration of the center of the cylinder with respect to the bottom of the loading compartment, that would be the instantaneous center. So instead of this equation here, we'll have to use this equation. That is the difference here, because here we are looking at the center. So this will be equal to minus 0.5 k cap cross 0.21 I cap plus 0.21 j cap, which will be equal to, if you solve both of these, you will finally get 0.106 I cap minus 0.106 j cap. Next, we shall be looking into the motion of the secondary reference xyz relative to the fixed reference capital XYZ. That means how this secondary reference frame here changes relative to the fixed reference frame capital XY. Now in this figure you can see that this corresponding truck here is moving towards left with some velocity, okay, and zero acceleration. So the reference frame the secondary reference frame small x small y will have a translational motion towards the left, since this entire truck is moving towards left. In addition to that, you see the xy reference frame at this instant of time is not only moving towards left with this corresponding velocity, it is also rotating with respect to this point here. We are required to find the velocity and acceleration when this cylinder here reaches at the bottom here. So as such, I can write r dot vector as the velocity of the truck plus the velocity due to the change in the angle of the compartment. For the time being, I'll call it as v theta here. Okay, so vt in the question, it is given as truck is moving at a constant speed of v equals 1.7 meter per second. So as such, vt will be equal to minus 1.7 into I cap. Now v theta, it is the velocity of the corresponding reference frame, secondary reference frame, small x small y, as this theta here changes. Okay, so that will be equal to theta dot cross d vector. This corresponding rotation here is what is expressed in this equation here. Okay, so theta dot here will be equal to minus 0.1 k cap cross, now d cap, d vector here, you can see that if xy reference frame with respect to this point will be in the negative x-axis. So as such, I can write this as minus 5 into I dash. Now here k dash and k are the same. I don't need to change here since both are oriented in the same direction. So as such, this will be equal to 0.5 into j dash cap meter per second, which I can express in terms of the fixed coordinates 0.5 into 0.707 I cap plus 0.707 j cap. Okay, so as such, my r dot vector will be equal to minus 1.7 I cap plus 0.5 into 0.707 will give me approximately 0.354 into I cap plus 0.354 into j cap. So if you solve this, you would get minus 1.346 into I cap plus 0.354 into j cap. The next is r double dot vector. Now r double dot vector as such will be equal to the translational acceleration towards the left plus, due to the corresponding rotation here, you will have an acceleration a theta. Now since the truck is moving with a constant velocity, at will be equal to 0. Okay, and a theta represents the rotation of center with respect to this point here. Okay, so as such, I can write the equation as alpha vector cross d vector plus omega vector cross omega vector cross d vector. Now alpha vector is actually theta double dot vector cross d vector plus omega vector is actually theta dot vector cross theta dot vector cross d vector. Now theta double dot will be equal to 0. So as such, this entire term will become 0. This I can write this. Now since this is a case of planar motion, I can write this as minus the magnitude of theta dot square multiplied by the d vector. So this will be equal to minus theta dot is having a magnitude 0.1. So this will become 0.01 multiplied by d vector. D vector, as I told you, it is minus 5 I dash. Okay, if you express this in terms of the fixed coordinates capital X capital Y, you would get 0.05 into 0.707 I cap minus 0.707 J cap. Now if you see the figure earlier, in this I dash, it is along this direction. So I dash will be equal to 0.707 along the positive x-axis and minus 0.0707 along the negative z-axis. So this is what is reflected here. So replacing it here, you would get AT, that is 0 plus 0.05 into 0.707 I cap minus 0.707 J cap, which if I solve, I will get 0.035 I cap minus 0.035 J cap. Moving on, next we shall concern ourselves with the motion of the center relative to capital XYZ. This is where we use the equations which we had studied in this lecture. So we have V capital XYZ vector is equal to V small xyz vector plus R dot vector plus omega vector cross rho vector. Now we had obtained all of these terms before, so I'll just write it down on the side here. V small xyz vector, we had obtained it as 0.21 I cap minus 0.21 J cap. R dot vector, we had obtained it as minus 1.346 I cap plus 0.354 J cap. And omega vector is actually the corresponding rotation of the reference frame, secondary reference frame XY relative to the fixed reference frame. So omega vector is actually theta dot vector, which in the question it is given as 0.1 into K cap. And finally rho vector, we had obtained it as 0.21 I cap plus 0.21 J cap. Now let me draw a line here. Now substituting all of these terms, we would get 0.21 I cap minus 0.21 J cap minus 1.346 I cap plus 0.354 J cap plus minus 0.1 K cap cross 0.21 I cap plus 0.21 J cap. So if you solve this, you would get minus 1.113 I cap plus 0.121 J cap meter per second. Similarly, we can obtain the corresponding acceleration of the center of the cylinder relative to the fixed reference capital XYZ, that is equal to A small xyz plus R double dot plus 2 omega vector cross V small xyz plus omega dot vector cross rho vector plus omega vector cross rho vector. Now all of these terms we have already obtained it earlier. I'll write it down here. A small xyz is equal to 0.106 I cap minus 0.106 J cap. R double dot vector is equal to 0.035 I cap minus 0.035 j cap. Omega vector is already know it is theta dot vector, okay, and vxyz also we already know it, and then we have omega dot vector. Omega dot vector actually represents theta double dot vector, which we know it is 0, and then rho vector is also given. So substituting all of these, we would get 0.106 I cap minus 0.106 j cap plus 0.035 I cap minus 0.035 j cap plus 2 into omega vector, that is equal to minus 0.1 k cap cross vxyz vector, that is equal to 0.21 I cap minus 0.21 j cap plus, now omega dot vector is 0, so 0. Now omega vector cross rho vector I can represent as minus the magnitude omega square into rho vector. Now I shall not do the detailed steps of all these. If you solve this equation, you would finally get the answer 0.0965 I cap minus 0.1855 j cap meter per second square. So this is the velocity and acceleration of the center relative to the fixed frame capital XYZ, or we can say relative to the ground. So with this we come to the end of this corresponding unit. If we have time, we may go for three-dimensional problems. Thank you all.